Okay. Hi, everybody. My name is Raúl Briceño. I'm a professor at Old Dominion University, which you can see one of the buildings here. I'm also a staff scientist at Jefferson Lab, which is a lab out here in Virginia. Both of these places are approximately 30 miles away from each other. So normally in normal times, I would be traveling. I would be at ODU 2 or 3 times a week, and at Jefferson Lab a couple times a week. So I divide my time between the two. Also, I figured while we're just getting to know each other, I would introduce my assistants, Jazzy, who's out in the back. She's a little fluff ball. Um, she's not good with equations, but she is good about forcing me to take breaks when needed. So, why don't we jump into today's lecture? I'm here to talk about spectroscopy on the lattice. Okay, great. So, my job is to give you a little bit of introduction on lattice spectroscopy. We're going to be together for 4 days. I think what I'm going to do is I'm basically just going to make videos that break up each one of the concepts somewhat into little pockets. These might translate into one video per class or multiple videos per class. We'll see how it goes. Okay. I figured I would start with an outline of the class. Um, it's a little loosey goosey. It's just basically just a guide us, just to give you a little sense of where we're gonna go. I hand wrote everything, so you're gonna have to get used to reading my chicken scratch. So sorry about that. And first, what we're going to do is give you a little motivation of why we need to think about few body physics. This is perhaps not the first thing that comes to mind when you're thinking about spectroscopy. And so I'm going to introduce this quite a bit. And so really what we're going to be talking about the first couple of days is about scattering theory, various different aspects of scattering theory. We're going to define scattering amplitudes diagrammatically. We're going to discuss a little bit about their analytic structure, and the need for partial wave projection. It's not going to be quite in this order, but basically these are the topics that we'll be touching on. And we'll be constructing some specific parameterizations for the scattering amplitude, so you can see some of the consequences of different choices and parameterizations. We'll have some exercises. We'll come back to this later. And after thinking about scattering amplitudes and the connection with spectroscopy, we're going to need to figure out how to extract said scattering amplitudes from lattice calculations. And the best way to do this is via the Lucier formalism, the so-called Lucier formalism. And so I'm going to tell you all about this. This is going to require us to understand how we can extract spectra from correlation functions, which is something that we'll touch on briefly, but Amy Nicholson is going to be discussing this extraction of spectra in much more detail, so I'm just going to gloss over some of the details. And eventually what I'm going to really focus on is a derivation of this Lucier formalism, which allows us to connect the spectrum that we obtain on the lattice to physical partial wave amplitudes. Okay, we're going to have some exercises associated with that. And then the last topic that I will touch on is not just the determination of purely hadronic amplitudes, but transition amplitudes, where you can have a single hadron coupling to two particle states via some current insertion. I will motivate the need for this, and the extraction of these amplitudes from lattice correlation functions. This is a formalism that goes typically by the name of Laurent Lelouch and Martin Lucier, and so we're going to be referring to it that way. Okay, so that's basically the outline, and so why don't we just jump in, and really I figured I would start by motivating the need for obtaining spectra on the lattice. And to do this, we need to just think about broadly, what does it mean to determine the spectrum of QCD, and what are the challenges associated with extracting the spectrum? And so for this, I figured what we can do is just crack open the PDG. So here's my PDG being cracked open. In fact, we can just pull it up. Let me just pull it up on my browser. And so if you look at the in the PDG, right, you have a list of particles of different kinds. If we look at the mesonic sector, so the mesonic and baryonic sector, of course, is the actual spectrum of QCD. After all, QCD is it's confining, right? So we don't have any free quarks and gluons. The states of the theory are bound states of quarks and gluons. So if we look at the mesonic sector, we can see that there's a bunch of different classes of states, whether it's light unflavored mesons, light unflavored, other types of light unflavored mesons, strange, charm, etc. And we can just look at the light unflavored mesons, and we see that states are essentially ordered partly by the quantum numbers, but mostly by their masses. And so you have states that are the lightest of which that we see is the pions. These are the lightest states of the theory. You have the charged pions, the neutral pions, and you have the etas, and then after that you have the F naught, rho, omega, etc. And so what I did is I created a little table. So if you look at, if you go into each one of these pages, what you will find is various different properties. The most important to us is going to be the mass. And for some of them we'll be looking closely at their decay widths as well and their decay mechanisms. So if we look at, for example, the pi plus, its main decay mode is it's to mu plus the mu neutrino. This is approximately 100% of the time that it decays to this. There's other mechanisms that is further suppressed, and so this predominantly decays weakly, okay, and its lifetime is in the order of 10 to the negative 8 seconds, okay. And so instead of going through each one of them, I would encourage you to do so. What I went ahead and did was I made a little table for some of the particular examples that I wanted to highlight, which is just essentially the first ones that appear in the PDG in the light unflavored mesons. And I could have looked at the story that I'm about to tell you. Essentially, I could have looked at the charm sector, the strange sector, baryons, and the story that emerges is pretty ubiquitous. So let's look at the pi plus, right? It has a mass of approximately 140 MeV. I already set the lifetime and its decay mechanism, okay? And so I'm just ignoring mechanisms that are much further suppressed, okay? And the pi zero, right? It's almost the same mass, right? It's very close to that of the pi plus. Its lifetime is even shorter, and this is because it decays via QED, right? It decays to 2 photons, and so this is the predominant decay, and this is an electromagnetic decay, and so because the weak force is weaker than the electromagnetic force, this number is bigger than this number because it's less probable for a particle that if it's allowed to decay via electromagnetic interactions as well as weak interactions, the electromagnetic interactions are stronger, and so it's preferably to go through that mechanism. Okay. So the eta, it's the next particle that appears, and now we start to see something. This already the story of a dominant decay. There being a single dominant decay for a given particle starts to get washed out a little bit. The story starts to get a little more complicated. The eta has a mass of approximately 550 MeV. Its lifetime is in the order of 10 to the negative 19, and it doesn't decay just electromagnetically via 2-photon decays, but it's also allowed to decay via 3 pions. And this is done via the strong interaction. And so the eta is unstable both via electricity and magnetism, but also via the strong interaction. If we then continue on to the next state, and so here I've created a color coding mechanism. So the weak is the purple, the QED decays are in blue, and then the strong are in green. Okay, and if we look at the next state, which is the 500 F naught, the F naught 500. Historically, this has been known as the sigma. This is a mass that is far less better under constrained, so it's less precisely constrained than the first 3 particles. Its lifetime or equivalently its decay width is also less constrained. And one thing that we see is that now this is a particle that decays predominantly via the strong interaction. And so this decays almost 100% of the times to 2 pions. Okay. And if we look at the next state, the rho, this has a mass of approximately 770 MeV with a decay width of 147 MeV. And so something to note of the lifetimes, right? I skipped over the F naught 500. This has a lifetime of the order of 10 to negative 24. Same thing for the rho. So it's a much smaller number. Its decay width are in the orders of hundreds of MeV, right? Versus for the eta is in the order of keVs. So this is a particle that lives for a long time, right? Many orders of magnitude more than these 2 particles, which decay predominantly to 2 particles and they decay via the strong interactions. Okay, and so if we want to understand, and what ends up happening is that if you look at all the other higher line states, they all end up decaying via the strong interaction. So most of the states in QCD are unstable under the strong interactions. And so most of the states are resonances that decay via the strong interaction. So of course, the standard model, it's a combination of QCD, the weak interaction, and QED. But many times in lattice calculations, what we do is that we turn off the electromagnetic and weak interaction, the electroweak sector. We turn it off, and we think about the theory of QCD on its own. And so, if we turn off these interactions, what we find, right, is that the pi plus and the pi zero have an infinite lifetime, meaning they're QCD stable, they never decay, since we would just exactly turn off these interactions. But that, having said that, the rest of the spectrum would continue to be unstable. The majority of the states would continue to decay either to 3 particles, 2 particles. The eta primes also decays to 3 particles, and we start looking into higher states like the F naught 980, which are still in this table that I pointed you to. They don't decay just to one channel, but they decay to multiple channels and many times with comparable strengths. Okay. And so if we want to understand the simplest consequences of any theory, namely the spectrum, and if we want to understand that for QCD, we necessarily have to think about unstable resonances that decay to multi-particle states. And so we have to, this is what we want to do. This is the simplest thing that we can do if we want to claim understanding of a theory like QCD. It turns out that this is a remarkably challenging problem because most of the states are strongly coupled to multi-particle states, and not just to one, but sometimes to multiple. And these decays may be to 2 particles or 3 particles. And sometimes these are equally strong. And so this is a remarkably challenging task, but it's not at all impossible. And so what we're going to talk about is how we do this rigorously as possible for at least resonances of decay to two particles. Okay. And so so this brings me to how do we even see these resonances experimentally? And one thing that I want to try to convey to you is the universality of resonances. So hadronic resonances are not just interesting on their own right, because they are the way that the spectrum gets manifested, right? But resonances appear in multiple byproducts in experimental searches. And whether it's just in the aims of trying to understand the strong interaction or electroweak sector, or even extensions of the standard model, many times we need to think about multi-particle byproducts where these multi-particle states can couple to hadronic resonances. And these hadronic resonances, of course, have to be universal for them to make any sense. For us to be able to think of them as states of a theory. And so here I figured I'd give you a little cartoon of how these may appear in various different experiments. So for example, at Jefferson Lab, where I reside, there we have an electron beam that interacts with a nuclear target, simplest of which is a proton, right? The electron and the proton interact via photon exchanges to simplest approximations, at least to interact via the exchange of a single photon to leading order, right? If this photon comes in with enough energy, it can create a intermediate resonance state, right? And if you keep track of the quantum numbers, right? So here, if this is a proton, I'm labeling this as a neutron, so this has to be a rho plus. This rho plus is short-lived, and eventually this decays onto two particles, and what we see is really these particles are the ones that eventually hit our detector. I mean, the pi knot might actually not hit your detector, so what you see is the photon decays. In COMPASS, which is located at CERN, there is actually a pion beam, and so there you can have reactions where you have a pion interacting with the proton target. Again, you would create the same intermediate rho, right? These two guys are the same, which ultimately would then decay to pions. At BEST 3, located in China, there what you have is a E plus E minus reaction. These electropositrons beams can annihilate each other, create a photon, which has the quantum numbers of the rho, which can then, in this case, since this is a neutral state, and the photon, of course, is neutral, this would have to be the rho naught, and so, but then that would decay to the isospin 1 combination of two pions, right? And so what you would see experimentally essentially would be event. So the simplest thing you can count, right, is a number of events, which is related to the cross section. And what you would see experimentally is a counting of number of events that you would detect in your detector as a function of energy. So here I'm plotting energy, where P is the form momentum that is being carried out by these two pions. I'm taking the square of that. That would be the energy squared scanning through that. That's a Lorentz. So that would be the form momentum square, which is a Lorentz scalar. So I can evaluate in the center mass energy. And what you would see experimentally is a little bump in the kinematic region where you have that state. And the width of this bump is roughly related to the decay width of the resonance. And so this is the warm and fuzzy intuition that we have for resonances, whether they're hadronic or not hadronic, right? They emerge as little bumps in cross sections in experiments. Okay, and so this is our warm and fuzzy story, right? But there's some complexities associated with this warm and fuzzy story, some caveats which we're gonna dive into. And so here are my set of remarks, some of which I've already said, but it's worth reiterating, right? The first one being that resonances are absolutely universal, right? They don't depend on how we produce them, right? They're all emergent from the interaction between the particles that interact. They could be they could appear as initial state interactions or final state interactions, but they're just they don't depend. They're universal. The presence, whether we see this bump, right, or not, does depend on the production mechanism, right? Because it could be that the production mechanism for this reaction, let's say over here, the pi plus and the proton, right? This could be dynamically suppressed, and so we may not be able to necessarily see these two pions, and instead what we would see is something more complicated where we need to create another pion, and this is indeed the case for compass. So in some cases it's hard to see some particles just because the coupling for the production mechanism is small. Okay, and so something that I've already stated, right, is that if we want to think about the spectrum, this forces us to think about resonances because they're unstable, and resonances emerge as a consequence of the interactions of two particles or more, and so this necessarily forces us to think about few body physics. Okay, and so what we'll do is define resonances rigorously, not a little beyond this like bumpy like picture that we all feel warm and fuzzy about. And so we're gonna dig into this, and something that I will touch on, that I will try to convey, is that although I am talking about resonances and bound states are actually continuously connected in QCD. As we dial the parameters of the theory, states that are resonant, they can become bound. And so if you're interested in the physics of, if you're interested in nuclear physics, for example, the interactions between protons and neutrons and the formation of the deuteron, if we dial the quark masses, it could be that these states become resonant. And so we're going to try to understand how this connection can be thought about. Okay. And so, give me a second. Okay, so then hopefully I convinced you that few body physics, we're forced to think about few body physics because of, the unstable nature of these particles, right? And because we're interested in few bodies, we necessarily have to dive into a story of scattering, some of which is very familiar to some of you and perhaps less familiar to some of you. And so I figured for the sake of completeness, I would just introduce concepts of scattering theory that are familiar to you, reiterate them so they sink in even deeper, and then I'll introduce concepts in scattering theory that are perhaps less familiar to some of you. Okay, so the building block, the object of our desire in the context of scattering theory, the most primordial object, let's say, is the S matrix. Okay, and so I can define the S matrix in terms of its matrix elements, which it couples incoming states with outgoing states. Okay, and this is nothing more than the okay, I just found a typo which I corrected. Of course, there should be a minus sign there. So we could define the S matrix elements as matrix elements of the time evolution operator, which connects states in the far past with states in the far future, where we take this t to infinity. Okay, and so something that already emerges, right, that you perhaps, knowing what you know about lattice QCD so far, right, or any lattice field theory, is that we're necessarily forced, or historically we've been forced to wick rotating the theory into Euclidean spacetime. So there we can do Monte Carlo sampling, well-defined Monte Carlo sampling of gauge fields, and so we can do statistical evaluation of correlation functions without having to make approximations about the dynamics, right? That's the beauty of lattice QCD. But here, of course, I'm already defining something that requires a need for real time, right? We need to define the S matrix, right? We need to have a real time evolution operator. And so this may seem impossible, and indeed, right, if we're restricted to purely imaginary time, in general, we can't access directly scattering amplitudes. Emphasis on directly, right? That's not possible, or at least in general, it's for some kinematics you may be able to do this, but for all kinematics, you can't directly access scattering amplitudes. And so what we're gonna use is a beautiful trick that allows us to circumvent this, which is using the spectra of the theory. We're able to extract the finite volume spectra very well. That's something that we can do very well these days. And so we can connect the finite volume spectra with the physical scattering amplitudes. And so that's where we're going. Okay. And so a couple other caveats, right, is that what we determine in lattice QCD is the spectrum of the theory. I think the spectra, okay, spectra of the theory for a given L and a given A. What do I mean by that? I imagine I've truncated, I made my space-time Euclidean, right, and I've truncated the theory to be in a finite box, right, and I'm only going to be thinking about box. We can construct more complicated geometries, but I'm just going to think about a qubit box of length L on each direction, and I have a mesh size inside of there, where all points are separated by some lattice spacing A. Okay, and so in my lectures, I'm gonna make my life easy, and I'm just gonna ignore the lattice spacing effects, or I'm just gonna assume that we've taken the continuum limit, or that we have some other mechanism to assess the discretization effects. Right, and so I'm only going to be thinking about IR effects. So I'm only going to be thinking about effects associated with the box. Okay, and this will become increasingly clear, I think, with the lectures. Okay, but if it isn't, put a pin on it and ask me about it in the discussion sessions. Okay, and so because I'm in a finite box, this necessarily discretizes the spectrum. Right, we know this quite well from quantum mechanics, and we're gonna, re-emphasize this in this set of lectures. So, I'm making some general statements that I take a little bit as a given, just refreshing your head about these concepts, and then we're gonna, say them enough that you believe it, and then hopefully at some point you understand it completely, right? And so, why is this the case? The case of why the spectrum changes, right? We went from in the infinite volume limit, we have a continuous spectrum, right? There's nothing that is separating one kinematic point versus another, right? But if we put it in a box, we already discretize the theory. And so you might ask, we discretize the spectrum. And so you might ask, isn't the Hamiltonian the same? Why is this happening? Well, no. What's the same, right, between the finite volume and the infinite volume world is the Hamiltonian density, right? To get from the Hamiltonian density to the Hamiltonian, right, you have to do an integration of the Hamiltonian over your box, and that already imposes some boundary conditions that changes everything, and so then this is the finite volume Hamiltonian itself does have discrete energy levels and discrete states. In these energy levels, right, we can enumerate them in n, from 0 all the way to whatever our cutoff is. And the states, the eigenvalues that emerge are going to depend on L. And so we're going to try to understand this L dependence. And this L dependence is going to be directly related to the infinite volume scattering amplitudes that we're after. That's going to be the punchlines. Okay? So, and so to give you a little bit of, a warm and fuzzy understanding of how this connection exists, right? This connection between the finite volume spectrum and the infinite volume amplitude, namely the finite volume spectrum and the desired infinite volume dynamics, right? It's worth to just think about a little perturbative argument about this, warm and fuzzy explanations, as I call it, okay? So the scattering amplitude, right? We know how to evaluate perturbatively. If you give me some effective field theory, some theory for QCD, I'm assuming some effective field theory, or let's forget about QCD for a second, any theory, right? Give me some interaction, right? Some potential density, and I I can evaluate from this potential density the, to leading order, I can obtain the scattering amplitude, right? Say for two particles, right? But given the same potential density, which is the same in a finite volume as an infinite volume, right? I can evaluate expectation values of this potential density in a finite volume. And this is, related directly to the spectrum of the theory of the same theory, but in a box, right? This would be a perturbative, a perturbative determination of the spectrum. But so what, right? That's the whole point. And so if I have a perturbative relationship between the potential and my spectrum, right? Well, and I have a perturbative relation between my potential and my scattering amplitude, that tells me that there has to be a relationship between these two, right? At least perturbatively, right? And so indeed, there is such a relationship between the finite volume spectrum and the scattering amplitude, at least perturbatively. And so what we're going to do in a couple set of lectures is derive with as much rigor as possible without exhausting you too much this relationship between the finite volume spectrum and the infinite volume scattering amplitude without using any perturbative expansion. Okay, so it's going to be more rigorous than that, because ultimately we want to do QCD non-perturbatively, right? And so that's what we're doing lattice QCD. We're investing all these computational resources to do hardcore non-perturbative physics, and so ultimately we want to make sure to have non-perturbative observable, and so we're gonna do the hard work, the theoretical hard work, to then match non-perturbatively the spectrum that we get and the desired infinite volume amplitudes. That's the goal. Okay, so the goal of what we're gonna do in the next lectures. Actually, why don't we do this? No, okay, let's okay. So the goal of the next two lectures is going to be to do a review of the consequences of unitarity for two-body systems. So this is a golden standard for understanding scattering amplitudes, okay? So I'm just going to review some aspects of scattering theory that are textbook to some extent that you're familiar with. I find this thesis by Andrew Jakura, who's a postdoc working with us at Old Dominion University, and he will be assisting you. His thesis on studies on multiparticle scattering theory from 2019 has a beautiful introduction for this, so I was using that as a cheat sheet, and I would encourage you to do the same. And then we're going to connect these like golden textbook rules with perhaps a new and a useful way to think about scattering amplitudes diagrammatically, where there are two references that I would point to you are a recent paper that I co-wrote with Andrew and Felipe Ortega Gama and Keegan Sherman, who are students at William & Mary and ODU, on the on-shell representation of two-body transition amplitudes. And a second reference is a pedagogical review that I co-wrote with Joe Dudek at William & Mary and Ross Young at Adelaide. It's a review on scattering processes from lattice QCD. So with that, I'm gonna pause for a second, and I'll let you go check out the next video. Okay.